In Class 1-2 of Gakuben Prefectural High School, one student had the entire school's attention from the very first day. He's stylish carrying out his class duties, he's stylish at lunchtime, and he's even stylish when sent to stand in the hall. Every single move he makes is cool, cooler, coolest. He lives an overwhelmingly cool, stylish high school life, and his name is Sakamoto. And that's how our character Sakamoto was introduced in the show. Haven't you heard? I'm Sakamoto. With Sakamoto being the coolest guy around, let's see one of his scenes and see if there's a secret that he's hiding to his magic.
お、帰ってきた。坂本。
Alright, first let's analyze the clip. We'll first solve for the length of the broom. And to find that length, we'll go to Amazon and search for brooms. And after searching Amazon, we can determine the average length of the broom to be 60 inches or 5 feet. And when we convert that into metric, we get 1.524 meters. The broomstick is centered on the barrel, so both sides are equidistant from the center at 0.762 meters each. The broom seems to be stuck to the barrel, so for the sake of simplicity, there is no friction between the broom and the barrel while it is tilting. Also, for the sake of simplicity, we'll ignore bending moment and the mass of the broom in the equation. So Sakamoto needs to reach the second floor window of the building, and the average height of a floor in Tokyo is 8 feet, but then there is also the flooring for the second floor, so let's add half a foot to be safe, and then add 2.5 feet for the window sill height since it is a standard, which in total would lead to 11 feet up, or equal to 3.3528 meters. Alright, we're going to want to solve for the initial velocity of Sakamoto when he leaves the broom. And for this, we're going to have to be solving for time first. And for time, we'll be solving it with the equation distance over acceleration equals time squared. For acceleration, we'll factor in acceleration due to gravity since that's the only acceleration acting on Sakamoto in flight. And for distance, we'll factor in the height of the windowsill since that's what we're trying to solve for. Alright, so we'll be putting 3.3528 meters or 9.81 meters per second squared and squaring that to solve for time, which would be 0.5846141 seconds. And now I'll be using that time given for the equation distance over time equals velocity. So it would be 3.3528 meters over the time we've just solved for, and now solve for 5.73506477731575 meters per second. Long number, but you get the point. So now, since we know the velocity at which Sakamoto is propelled up, we need to know the force that was exerted on him to get him at that velocity. For that, we need his mass, but here's the unknown variable: nobody knows his mass. Sakamoto is generally a weird person in general. We don't know a lot about him. We don't know much other than his last name, which is Sakamoto, and that he goes to that high school. Nobody knows his weight, his birthday, or anything about the sort. Everything was kept a secret by the author. So to find his weight, we're just going to solve for the weight of the rock instead. And to find that, we're going to use the density of the rock, which is 2.65 grams per centimeter squared. And yet again, we'll be going to Amazon to find the average surface area for a broom such as the one shown. And with our research, we find that it's at 1 foot wide, and since it appears to be square in the scene shown, we'll also make the length 1 foot wide. And now we'll solve for the volume of the ellipsoid rock, for which the equation is 4/3 pi ABC. A standing for length, B standing for thickness, and C standing for height. As shown by the still put onto the screen now, we're going to split the broom into halves to see how big the broom actually is. And we'll split into another half, and into another half. And from then on, now we can see how big the rock is compared to the broom. From the guidelines, we can see that the rock is 1/8 of the broom length away from the edge. And since it's going to be the same on the other side, we can determine that's going to be 2/8, and from that we determine that it's 1/4. So rock is 75% of the length of the broom. Alright, since we just solved for the length of the rock, now we can solve for the width of it. And from that, we can see that it lines up fairly well with the other ends of the broom, and we'll just say that's going to be 1 foot wide from that. Now we're going to solve for the last measurement of the rock using this still. We will set a line down the middle of the rock and use that to proportionally figure out the width of the rock using image editing software. And with the image editing software, we can see that the horizontal line is 67.3% of the length of the vertical line, which would put it at 0.504807767 feet. Now since we have all our measurements in feet, we must convert them into meters. So our 1 foot width turns to 2.3048 meters, our 0.75 feet width turns to 0.2286 meters, and our width that we just solved for turns to 2.1539 meters. Now we must use the formula 4/3 pi ABC, which would solve for volume, which would equal 0.044907689448154 meters cubic. And then we must turn it into centimeters cubic to match up with our density 2.65 grams per cubic centimeter. So we must times it by 1 million to be able to get 44,907.689. Now we must just times that with our density 2.65 grams per cubic centimeter and divide that by 1000 to get it in kilograms, which would equal 119 kilograms. The height at which the rock falls from is the same as the one Sakamoto jumps to, and since Sakamoto is the same distance from the center of the room as the rock, if we ignore air resistance, that means Sakamoto must weigh 119 kilograms. I think we found Sakamoto's little secret that he was hiding. At 119 kilograms, you'd be probably morbidly obese. And that concludes the analysis of my physics of Sakamoto desu ga, or haven't you heard, Sakamoto as is better known. And do I think the physics are good? Probably not.